In this part, we discuss force acting on a current carrying conductor placed in a uniform magnetic field. So, this is the situation where a uniform magnetic field is shown here by drawing equally spaced parallel lines. And in that uniform magnetic field V, a conductor of length L and area of cross section A carrying steady current I is placed as shown at an angle theta with the direction of the magnetic field. Now, you can find that as the conductor is kept like this in the field, it is found to be shifted because of a force acting on it. Now, in this part, we want to discuss how the force is acting or how a force is derived on the current carrying conductor placed in the uniform magnetic field. Now, here, the current is constituted by the movement of free electrons through the conductor, and the free electrons are moving along this direction. Free electrons are moving downward, then only the current goes up. Now, each free electron, as it is moving through this part, will be acted upon by a magnetic force called magnetic Lorentz force. So that magnetic Lorentz force, I can write it as F equal to E into V D cross B, I can say. Now I am taking the positive charge counterpart for the constitution of current here. Therefore, I have taken that plus E here as it is moving. Now, as the number of charges is flowing, then one charge is experiencing a force small f, then there will be n number of free electrons or free charges moving through the conductor to constitute current. Therefore, there will be a total force F acting that will be equal to n times the force experienced by one charge. That is equal to n times E into V D cross B, I can say, where Vd is called the drift velocity that we discussed in current electricity. Now, if you substitute for that n number of charges from the number density of free electrons, we get that F to be equal to small n into volume of the conductor, as the small n represents the number per unit volume. So, small n into volume of the conductor into E into Vd cross B, I can take. I will make a small variation here. The L, I bring it over here because both are along the same. Therefore, I can rewrite this to be equal to NEA into VD into L cross B, I could write. Now, this NEA into VD is the magnitude of the current flowing, and therefore the force F acting on it will be equal to I into L cross B, I can write. So this I into L, I am taking it as a vector, and that vector is the direction of alignment of this conductor carrying current, and therefore this is the total force acting on the n number of charges moving through the conductor to constitute current, and effectively that total force will be acting on the conductor and the conductor will be moving through the magnetic field. So, force acting on the current carrying conductor is now equal to F, which is equal to IL cross B, or F equal to I into B into L sin theta. Okay. Now, the direction of this force is again obtained by the Fleming's left hand rule, as we have applied it for the force acting on a charge moving through the magnetic field. That is, Fleming's left hand rule, you hold the left hand, 3 fingers, middle finger, forefinger and the thumb, in such a way that the forefinger shows the magnetic field direction and the middle finger shows the direction in which the current flowing, then thumb will be pointing towards the direction of the force acting on the conductor. So like this, you can find the direction of the force acting. That force will be both perpendicular to the direction of flow of current and direction of the magnetic field. And you can arrive at a maximum force condition and a zero force condition from this. That maximum force is obtained. Maximum force is obtained in this case, which is when theta equal to 90 degree, that F maximum will be equal to I into L into B. When theta equal to 90 degree, that means that the conductor will be exactly perpendicular to the direction of the magnetic field. Then there will be a minimum force condition, that is when theta equal to 0 degree or 180 degree. In these two cases, you can see that the F will be equal to 0. Now, the sin theta, that defines whether the force must be 0 or the force must be maximum. When you say this condition, the conductor will be like parallel or anti-parallel with the magnetic field. Okay? And you can see one resemblance here with the magnetic Lorentz force in the case of charge moving. The same thing is coming in the case of force acting on the current carrying conductor, because both these two forces are one and the same, that is magnetic Lorentz force. Okay? So when a conductor is placed in a uniform magnetic field and if you set a current flowing through it, then definitely a force will be acting on it. Now this idea is applied in the making of motors, electric motors. But unfortunately we are not discussing that in the +2 level. Okay, thank you.